Until now, we've focused on how magnetic fields affect moving charges and electric currents, and now we're going to switch that around and we're going to talk about how moving charges and currents create magnetic fields. If there's a charge moving near a magnet, the magnet can exert a force on the charge through its magnetic field. But according to Newton's law, if the magnet through its magnetic field is exerting a force on the moving charge, then the moving charge also needs to exert an equal but opposite force on the magnet. The origin of this reaction force on the magnet can't be electric or gravitational, because if either of those was significant, it couldn't point in the necessary direction. So the only force left to us is a magnetic force. This moving charge exerts a magnetic force on the magnet, just like the magnet exerts a magnetic force on the moving charge. For that to be true, the moving charge must generate a magnetic field of its own. We can actually use this example to figure out what the shape of the magnetic field created by this moving charge is. For example, the north pole of this magnet has to be pushed into the board, or I guess into the screen in this case. And north poles of magnets experience forces in the direction of the fields they're exposed to, just like a compass. That means that at the position of the north pole of this magnet, the magnetic field created by the moving charge has to be into the screen. Now, if we move this magnet to the other side, keeping the north pole closest, then the moving charge would experience a force into the screen, meaning the magnet would now experience a force out of the screen, which means the magnetic field caused by the moving charge at the position of this north pole has to be pointing outwards. And if we place the magnet behind or directly in front of the moving charge would experience no force because the cross product of V cross B would be 0. And the only way for the moving charge to exert no force on the magnet in turn is for the moving charge's magnetic field at those locations to be 0. Because a magnet will experience a force in the direction of the magnetic field no matter what. It's not like a moving charge in that sense. By extending this logic into 3 dimensions, we can conclude that the magnetic field of a moving charge wraps around the moving charge in a plane perpendicular to its direction of motion. So far we've done all of this in the context of a single moving charge, but we can generalize this straightforwardly to current through an extended wire. All it really changes is that the magnetic field now exists along the entire length of the wire, but it still exhibits this same kind of wrapping behavior. This actually gives us a new right-hand rule that we can use to very quickly determine the direction of the magnetic field created by a moving charge or current. All you do is point your thumb in the direction of the electric current and you curl your fingers around it, and the direction that your fingers curl represents the direction of the magnetic field. One thing to watch out for is if you're doing this for a single moving negative charge like in an electron, if you point your thumb in the direction the electron is moving, you will have to then flip the result because the current is actually in the opposite direction of the motion of a negative charge. So that's one thing to watch out for. This is a commonality of all right-hand rules. Whenever you work with negative charges, you always have to flip the result. Now that we have the direction of the magnetic field created by moving charges and currents, the next obvious question is, how do we figure out the strength of the magnetic field? And this turns out to be a far sight trickier to do. This is most often done by measuring the forces between 2 current-carrying wires. If we can measure the forces on the 2 wires, we can actually use that to calculate the magnetic field needed to exert that particular force, using what we learned in the previous lessons. And then we can relate that to the amount of current in the wires, and we end up with the relationship between the amount of current flowing and the strength of the magnetic field. And the result is called the Biot-Savart Law. If you have trouble pronouncing this, imagine you forgot what sound the letter T makes and then mispronounce the word bio. Imagine you have a wire segment like this with some electric current flowing through it. If I want to find the magnetic field at some arbitrary point in space, let's call it P, I need to consider the effects of the current along each little segment of this wire. As an example, let's consider this particular little section in red. This little section is defined by 2 things, a length and a direction. In reality, this particular section of wire might be curving a little bit, but if we do our normal thing in calculus and take the limit as this section approaches 0 length, then the directionality becomes very well defined. Our point P is a certain distance r away from the section of wire, and usually in order to make the math that we're going to do in a minute a little bit cleaner, we write this displacement vector r as the magnitude, the distance, times a unit vector r hat that points in the same direction. It really means the same thing. The unit vector r hat can always be expressed as the vector r divided by its magnitude. And finally, we have the angle between ds and r. I shouldn't have said finally because we can actually just use our new right-hand rule to determine the direction of the magnetic field due to this little section as well. So if we point our thumb in the direction of ds and we curl our fingers around, we find that on this side of the wire where point P is from this little section, our fingers point into the screen. So at point P, the magnetic field from this small section of wire points into the screen. We can use all this geometric information to write down the Biot-Savart law, which gives us the value of dB, the component of the magnetic field due to this one small section of wire. There is quite a lot to talk about here. One thing that you can notice very quickly, though, is that the cross product of ds with r, according to our original right-hand rule for cross products, does indeed give us a direction into the screen consistent with the direction of the magnetic field that we determined from our new right-hand rule. As I said earlier, the inclusion of r hat here instead of just the r vector is there because it often makes our work a little bit easier. Sometimes that's not the case though, and it's easier to leave everything in terms of the original vector r. We can do this by simply replacing r hat with the original vector r, but then we add an additional power of the distance in the denominator. Mu naught is a constant. It's called the permeability constant, and it has a value of 4 pi times 10 to the minus 7 Tesla meters per ampere. It is completely analogous to the permittivity constant epsilon naught for electric forces. And in fact, the Biot-Savart law can be thought of as Coulomb's law for magnetism. It has a very similar form. In the denominator, we have 4 pi r squared, just like we have for electrostatics. We have a permeability constant instead of a permittivity constant. And the numerator is where things get a little bit different. Coulomb's law is simpler because the only thing that determines that matters for an electric field is how much charge and where is it. But for magnetic fields, what we care about is how is charge moving, and that means how much charge is moving, how quickly is it moving, and in what direction is it moving. Magnetic fields are more complicated because it has this directional dependence on the source of the field. In practice, when we use this, we often calculate magnitudes mathematically and we put directions in by hand using our right-hand rules. In that context, it's convenient to also write down a simpler expression for the magnitude of dB, ignoring its direction. In order to do that, we need to evaluate this cross product, and we take only the magnitude information and we throw away the direction. Well, the cross product of two vectors is equal to the product of their magnitude times the sine of the angle between them. And so the cross product between ds and r hat, well, r hat has a magnitude of 1, and so it simply gives us the magnitude of ds times 1 times the sine of the angle between them. And just as an additional confirmation, in any of these forms of the Biot-Savart law, we can also see that if we look at a point directly in front of or behind the current, the magnetic field dB due to that section of our current carrying wire will be 0. And the reason for that, well, if point P is over here, then theta would be 0, and the sine of 0 is 0, and so dB would be 0. Or alternatively, the cross product between two vectors that are pointing in the same direction is 0. The simplest application of the Biot-Savart law is to calculate the magnetic field everywhere due to a long or infinitely long current carrying wire. We can do this in much the same way that we calculated the electric field due to an infinitely long length of charge. So let's pick a random point P to find the magnetic field, and let's consider the effect from some arbitrary length of our wire, ds. ds is a distance r away from point P with a unit vector r hat, and there is an angle theta between ds and r hat. Additionally, I'm going to call the distance between the wire and point P capital R, and the section represented by ds is a distance s away from point P in the direction of the wire. Finally, using the right-hand rule along any part of our wire, or by using understanding of the cross product, we can also establish that the magnetic field at point P must be pointing into the page. So now we can write down that the magnitude of dB is equal to mu naught over 4 pi times the current times ds times sine of theta over r squared. To find the total magnetic field at point P, we then have to integrate this expression from s equals minus infinity to s equals positive infinity along the entire length of this wire. We can actually simplify this a little bit by writing it as twice the integral over half the wire, because the integral from 0 to infinity will give us the same contribution as from negative infinity to 0. Substituting in the expression for dB makes it clear that we still have a bit of work to do, because we're integrating over ds, but we have this pesky theta and lowercase r floating around, and both of those are functions of s. As we've done before, we can rewrite lowercase r in terms of capital R, which is a constant, and the integration variable s. To get rid of theta, we can identify this angle here as the supplement of theta, and the sine of an angle is equal to the sine of its supplement, and the sine of this supplemental angle is equal to the opposite side of the triangle divided by the hypotenuse. And of course, we can rewrite lowercase r as we did above in terms of capital R and the integration variable s. Now we can rewrite our integral in terms of just constants and our integration variable s by getting rid of theta and lowercase r. We've seen exactly this kind of integral before. We can solve it using trig substitution, or we can just look it up, or we can use an integral calculator or something. When you work it out, you end up with this expression, and when you evaluate the upper and lower bounds, we get mu naught times I over 2 pi r. This is the value of the magnetic field created by a long length of current at a distance r from the length of wire. It doesn't matter where along the length you are as long as you are very far from either of the ends. This is almost exactly the same expression as the electric field for a long length of charge. The only difference is that we have the charge density instead of the electric current, and the permeability is in the numerator, whereas the permittivity for electric fields is in the denominator. While in most ways this calculation does almost completely resemble the calculation we did for electric fields of a long length of charge density, there is an important distinction. When we did this for electric fields, we used symmetry to argue that the vertical components of the electric field would cancel out, and so all we did was we counted the horizontal component. But in the case with magnetic fields, the component of the magnetic field from every single tiny length along this wire is pointing in the same direction, into the screen. We didn't have to rely on symmetry letting us cancel things out to 0. We actually calculated the component from every section and added them all up together. Something this allows us to do that we couldn't do with electric fields is we can say, well, what if we simply didn't have the lower half of this wire or the upper half of this wire? Let me just get rid of it. Well, that just means I have half the contribution that I had before. So if I have a length of wire that's semi-infinite, that has a starting point but doesn't have an ending point, then the magnetic field of that wire is just 1/2 of the magnetic field of the infinitely long wire in both directions. And so we can simply write that as mu naught I over 4 pi r. And you may recall that calculating the electric field due to an arbitrary length of charge was kind of complicated. Unless the point we cared about had a lot of symmetry relative to the length of charge we were working with, it was very, very hard to do. We ended up with integrals that were just really ugly. But with magnetic fields, it tends to actually be simpler because we don't really have to rely very much on symmetry at all. The integral just is simpler. Another really useful example to talk about is a circular arc of current. As with electric fields, we'll only be concerned with the magnetic field at the center of the arc. We can actually work out the direction first by once again making use of the right-hand rule. If you point your thumb tangent to this arc of current in the direction of the current, and you wrap your fingers around, you'll always find that your fingers are pointing out of the screen at point P. we can label some arbitrary length of our arc as ds. That arc is always a distance r away because point P is at the center of this arc. And the angle between ds and dr is always 90 degrees. Since we already found the direction of dB for each of these infinitesimal arcs, we can write down its magnitude the same way we have before using Biot-Savart. But this time we don't have to worry about theta at all. Theta is 90 degrees, always. Likewise, r is just the radius of the circle, and that's just constant too, so we can replace that as well. And ds is a length of arc, and so we can rewrite ds as r, capital R, times d phi. The total magnetic field then can be written as the integral of dB, where almost everything in dB now is just a constant. And this integral gives us mu naught times I times the angle subtended by the arc over 4 pi times the radius. Keep in mind that phi must be given in radians because we made use of this arc length formula over here that assumes that the angle is in radians. And so the result is we have a magnetic field with this value pointing towards you or out of the screen at point P, the center of the arc. This does not work if you're off center. If we were over here or over here or over here, this immediately becomes an incredibly hard problem. So we will never really be worrying about arcs unless we are actually at the center point. There are some other fun things we can do. For example, we could say, what if we added little legs to the end of this arc going outwards? After thinking about it for a little, and without doing any math, we can conclude that there would be no change. Just as we saw in the beginning of this video, current does not generate a magnetic field directly ahead of or behind it. So here the current is going this way, which means it doesn't generate a magnetic field in a line behind it or in front of it. Likewise, over here, there is no magnetic field over here. So these legs actually don't add anything to the problem. They are a deflection. All you really need to worry about is this length of arc. So just like with calculating electric fields of different configurations of charges, with magnetism, it also often helps to consider the various symmetries and arrangements of things, because you can very frequently say, oh, well, I can basically just calculate the magnetic field by multiplying by the angle of the arc, or I can ignore these because they won't do anything, and so on. This is all you need to know about calculating the magnetic field. Sorry. Pablo's going wild. All right. This is really all you need to know about the physics of calculating the magnetic field caused by steady electric current. Obviously, we can only do it for relatively simple shapes of wires, but in order to do anything more complicated, all you really need is more math. You need to learn more ways of doing math. You need to learn different methods of calculating more complicated integrals and so on. There's no more physics to learn about this. This is really it.